Good morning, gang. So today, we're going to pick up where we said we would last week. We're going to be talking about volume problems. Let me get the stock cam all set up. There we go. Today is the 31st of August. So, a few things, I guess. First, I wanted to talk a little bit about attendance. A reminder, attendance is mandatory. That means coming to these Zoom lectures. So I'm preaching to the choir. There's not an attendance component to the grade, but you do have to come. You're required to come. If you don't come to these lectures, things will not go well. It's as simple as that. Also, for financial aid purposes, I have to report whether or not you've attended. And the way I do that is by using those Zoom logs. So for financial aid purposes, I need to take attendance. And I do this through Zoom logs. So please use your real name. Zoom. Or if you're going to use a pseudonym or something, a handle of some sort, make sure I can discern your real name from that. So it's not the end of the world if you know you wanted to use like Connor C or Pablo A, that's fine. I can tell who you are from that. You can look and see in eStaff whether or not you have been reported as having attended class. And if you have been reported as having attended class, that means when I look at my Zoom log, I can tell, you know, who was who. I compare the Zoom log to my roster, and if you've got an abbreviation or something like that, most folks I think I was able to get in. But if you're still showing as having not attended in your eSanta Fe, when you look at your schedule, it'll show you like has attended, has not attended. Then I need you to make sure you reestablish the Zoom connection with either your real name or a name from which I can discern your real name. So if you want to use initials or like first initial, last name, or first name, last initial, that sort of thing should work okay also. But please make sure you do that. You don't actually need to type here in chat because at the end of all this, I record everybody who's come, and I can look at unique users, IP addresses, all that good shit. So just being present and having your name in Zoom be something similar to your real name is enough for this. But it is important, right? Coming to the Zoom lecture is critical because it gives you the opportunity to ask questions and to think on your feet with me. That's the big thing, right? Is that as we go through this material, you're gonna have these click moments where all of a sudden shit will fall into place and you'll be like, oh yeah, that works. I need you to be having those moments with me in real time. So that's crucial. I did get a handful of emails after I posted that announcement over the weekend, but I haven't had time to read all of them yet this morning. So I don't think I've read your email, Matthew, but I can turn off my screen share here. So yeah, I don't want everybody seeing my inbox. But I can see if I did receive that. Yeah, I did. So I'll go in there and take a look, Matthew. If your name as you're registered with Santa Fe is anything other than what you have in your Zoom or what you've sent me here in your email, I'll need that information. But I think as long as it's similar or discernible from that, I'll be able to add you there. Okay. So let's turn this back on. Back over here. Any other questions about attendance stuff? Okay, so today, the main thing we're going to be talking about is volumes. I'll cover section 6.2 today, and section 6.2 is on the method of slicing, and also the method of disks and washers. And they're two slightly different, but in an essential way connected. The slicing method is more general, and the disks washers method is equivalent to the slicing method, but it only works in certain cases. I'd like to start with the slicing method. And then on Wednesday, I'll introduce the methods from 6.3, and on Friday, we'll practice more with those. So let's look at a motivating example. I want to warn you, there is a lot of like drawing 3D stuff in these sections, and it's kind of tricky. My art is bad and I feel bad, but I will do my very best for you. I just ask that you be patient. I'll flip back to the textbook from time to time. So imagine I have some solid, maybe it looks like this. Something like that. And I'd like to find its volume. One way I can do this is by first putting an axis through it. I'll call that the x-axis. So this object here is a solid thing, like a lump of clay or something like that, right? I want to find its volume. And what I'm going to do is I'm going to imagine taking a little slice. This little slice has a thickness, which I'll call dx, because it's a thickness that's kind of spread out over the x-axis. And if I look at just that little slice on its own, it has a volume. So this dimension here is what I call dx, the thickness of the slice. And the main idea here is that I'm taking that slice to be so very thin that I can assume that the surface area, or just the cross-sectional area, is constant throughout that slice. So the area of the cross-section I'll call A of X, because I'm imagining slicing at a particular point along the x-axis, an arbitrary point that I'll call X. So you take your solid, you poke it through with a coordinate axis, you pick a point along that coordinate axis, and then you take a slice there. The area of the cross-section that you slice out, we'll call that A of X. And that means that the volume of this little guy, I'll call the total volume of the solid, V, then the volume of this little piece the volume of the little dx thickness piece I'll call dV, little differential volume, full volume. dV is the area of this little disk, the area of this little slice, times its thickness. So that's A of x times dx. And then you can think of this whole solid here as being made up of a bunch of little dx thickness slices. Your book does a good job of depicting this. So let me switch over to that for just a second. Here, right? Their blob is a little different than my blob. But you imagine taking a slice at some particular x value. You come up with the area of that slice. And then you add up all of those little slice areas, all those little slice volumes, right? Because the slice volume is just the area times the thickness. You add all of those up and that'll give you the volume. So the thing that we're going to integrate always, we're going to integrate dV to get V. So I imagine maybe over here, this is x equals A, and over here, this is x equals B. So my solid begins at x equals A and ends at x equals B. Sorry, I gotta turn something off in the next room. So I want to add up all those little dV volumes, all those little dV slices from x equals A to x equals B. And the way you do that is with an integral. So V is the integral from A to B of dV. That will always be true. And then in this method of slicing, that's the same as saying the integral from A to B times your area function dx. So this is what we call the method of slicing. We take a slice at an arbitrary location in my solid. You find the area of that cross section. You multiply by the thickness of that little differential cross section. And then you add all of those up with an integral. So this is basically how the method of slicing and also the method of disks works. The disk thing I'll show you as a special case of the slicing thing, but before we do that, I want to do an actual problem with this slicing method to see how we're feeling. Imagine I have a cone. Actually, let's do the pyramid. Let's find the volume of a pyramid whose square base has side lengths call them capital L, and height, we'll call it H. So, you can try to draw this pyramid. I'll draw it small over here at first, and then I'm going to draw a much bigger one a little later. All right. So this is L, and then the height in here, that's H. I'm drawing this little right angle here to show that the height is coming straight off the base. So I want to find the volume of this object. I can imagine poking through with a coordinate axis and trying to take a slice perpendicular to that coordinate axis. But I think before I do that, it would be easier for me to turn the whole picture on its side. So let me do that. So this is my base turned up on its side. Each of these side lengths is L. And then I'll come out here some amount to define the height. Drawing 3D stuff is hard. I'm not good at it, but I will do my best for you. Okay, here's this pyramid sitting on its side. Each of these lengths is capital L. And I'm going to imagine kind of poking through this pyramid straight from the middle of its base down here. Try to do this in a way that looks good. With a coordinate axis. We'll call this the x-axis. What I want to do is take a little slice. I want to come in here and slice a little portion of this pyramid out. So I come in like this, and I take my little slice. That slice has a little thickness. Let's see, it goes to there. This goes down to here, like this. Okay. So the thickness of my slice, that's dx. It's being taken at an x value in here that is arbitrary. We just call it x. And what I need to do is find the volume of this little slice. So I'll draw the slice now on its own. Since the base of the pyramid is a square, the slice will be a square slice. Or the larger dimensions here will be square. But I don't know what that larger dimension is. Again, this is dx, the thickness. But this guy changes. I know that those are equal to each other, so I'll label them both as little l. I know that those are equal to each other because the base of the pyramid being square means any cross section will also be square. So this is also L, this is also L. So the slice is a little square prism. It's like a little tile, a little block. dV, the volume of that slice, is going to be the height times the width times the depth. So that's L times L is L squared times dx. But the catch here is that little l actually changes. If you're all the way out at the tip of the pyramid here, little l is 0. And if you're all the way out at the base of the pyramid here, little l is equal to big L. Can everybody see what I'm saying there? See where the pieces are coming from? I want to take a second here. Well, it would mean at the tip, yeah. So right up there at the tip, little l is 0. It would say it's like a shrinking square, right? As I move this slice towards the tip, the square is shrinking down and down and down. It will always be square shaped until you get to the tip where it actually disappears. Right there at the tip, you don't actually have a square anymore, you have a point, I guess. So you have a 0-dimensional object. But the idea is that depending on where you slice, right, depending on what x value you're looking at, that slice might be large, like it would be up here, or it might be very small, like it would be up here. And we need to find the size of the slice as a function of where you're taking the slice. So I would say where L equals L of X changes depending on where we slice. Where we slice is X. So down here at the base of the pyramid, I'll call this X equals 0. And up here at the end of the pyramid, I'll call that X equals H because my pyramid is supposed to be of height H. So once I find the formula for little l, I'll just integrate dv from x equals 0 to x equals h. Do you feel like we understand the kind of strategy? It is a little bit complicated. I'll concede that. It's not obvious. The trick to coming up with the formula for little l is to look side on. So if I look just at the side, here is h. Here is x where I'm slicing. We're going to use a similar triangles argument. I know that this distance here is L, capital L. Because this is the base of my pyramid, right? I'm just looking straight on the side here. And my little l that I want is this. And what you'll notice is that, maybe not notice, maybe you will, is that this little triangle, whose back end here is the length that I want, is similar to the large triangle. So remember, this right here is x equals 0. This right here is x equals h. And remember, a triangle that is inscribed within another triangle is necessarily going to be similar to the larger triangle. So this little triangle is similar to this big triangle. Can everybody see that? The bold little triangle in here is similar to the big triangle here. So by similar triangles, this over this, which is capital L over capital H, has to be equal to this over this. Well, this is little l. That's good. That's what I want. what is this distance here from x to h? So this distance from here to here, that's h. This distance here, that's x. So this has to be h minus x. So what we're doing is we're saying that this over this has to be equal to this over this by similar triangles. This is big L, so big L over h must be equal to little l over h minus x. This will let me solve for little l. If you cross multiply, you multiply both sides by h minus x, you'll get little l is equal to capital L over h times parentheses h minus x. And now I can plug this in to my dV. Right? The area here is clearly L squared, and that L is a function of x. If I plug that in, I'll find that dV is little l squared, so that's capital L over h times h minus x all squared times dx. You can write that as L squared over h squared times h minus x squared dx. Therefore, the volume V, these three dots arranged in a triangle stand for the word therefore. dV is the integral, V is the integral of dV. And I'm going to integrate from x equals 0 all the way out to x equals h. I'm imagining this slice as moving through this pyramid. It will sweep out this pyramid as I move from x equals 0 to x equals h. So I integrate from 0 to h. And then I just plug in, okay, what was dV? dV was the thing we just figured out. So this is the integral from 0 to h of capital L squared over h squared times h minus x quantity squared dx. And from here, it's a fairly easy integral. We're just going to pop this constant out. We're going to FOIL this out. We'll use the power rule. So all the hard work in this problem is done at this point. So I'd like to pause here a minute before we do the integral, because the integral is easy, but this stuff that we've just done is hard. To take questions. So how do you guys feel about this?
Are you gonna have to come up with the 3D figures, or are we gonna be? Are you gonna give us that?
I will ask you to sketch things from time to time. Most of the problems we're going to do will have a lot of rotational symmetry, and I'll show you a shortcut for how to handle those where you don't have to necessarily draw the whole 3D figure, but I want you to do your best. Being able to visualize the 3D figures and being able to see them as stacks of slices and integrals like this is important. So I do want you to practice drawing these, and there will be problems on the test where I ask you to sketch one or another thing kind of like this.
Why did you square the dV for the equation?
Say that again?
Why'd you square the L over h minus x?
So our dV, we were able to determine, is the square of this side length, right? Because my little slice is a square. So the area is this times this. And since both of those are little l, the area here, this area, is L squared. So the volume of this little slice is L times dx, or L squared times dx. Does that make sense?
Yeah.
So I want to find the formula for the volume of a slice, and then integrate that. The volume of the slice is dv, and that's L times dx. So that's L squared times dx. I usually find it useful to come off to the side and just draw the little slice on its own. That's where I was able to cook that up. So in this picture, this is L, right? And I've labeled it over here where I have space. And then we use the similar triangle argument to figure out what little l is. This is, I think, probably the hard part. So you have to have this intuition to look side on and use the symmetry. And then notice that the big triangle here and the little triangle determined by our slice are actually similar. So this over this is the same as this over this. So that's big L over H. This over this is the same as this little l over this, which is h minus x. That gave us our formula for little l, and then we took that and plugged it back in here. So we know that dv is little l squared times dx. I know that little l is this, so dv is that squared times dx. Does that help?
Yes, thank you.
Okay, cool. Any other questions with how we got to this volume integral down here? Yes, H and capital L are constants. H is the height of the pyramid. Capital L is the length of the square base, which means L squared over H squared is a constant, so I can pop him out. And I'm just left with this integral. We could make a little silly substitution, u equals h minus x. But why do that when we could just FOIL it out? We might as well just FOIL it out. So I'm going to continue this on the next line. My capital L squared over h squared is going to come along for the ride. Integral 0 to h comes along for the ride. And if I FOIL this out, I'll get h squared minus 2hx plus x squared dx. And now I'm ready for my
Is that minus 2hx or plus?
Minus, because this is a minus here. So you can check if you FOIL this out, you'll have h times h minus x times h minus x. Your firsts will be h times h. Your inners and outers will both be minus x times h. And then your last will be minus x times minus x. So this will be a minus 2h times x, and then this will be a plus x squared. So if you want to come off to the side and take the time to FOIL this out, you can. There's no harm in doing that. Just make sure it doesn't get in the way of the workflow. Pablo asks a good question. For problems similar to this, do I recommend that you do this thing where you look side on? That's definitely the part here that requires like a bit of a creative step. You want to always exploit whatever symmetry you have. That I will say. And you may remember me saying at the end of class last week that we're going to be kind of thinking like physicists this week. That's what I mean. So physicists are obsessed with exploiting symmetry. That's what they do all the time because real world problems are very challenging unless you exploit symmetry. So the type of symmetry we have here is a sort of not quite rotational symmetry. It's kind of a planar symmetry. So the choice to look straight on from one side is exploiting that sort of planar symmetry. Let's go ahead and do our antiderivative step now. We're integrating dx, so h squared, this is a constant. He'll integrate to h squared times x. minus 2hx, the x here will integrate to x squared over 2, and the 2's will cancel. So we'll get minus hx squared. And then the x squared will integrate to 1/3 x cubed. And all of this is to be evaluated between x equals 0 and x equals h. If I plug in 0, everything here is 0. All right, if I plug in 0 for x, all three terms go away. So the only contribution comes from the upper bound. And when I plug in h for x, I'll get L squared over h squared out front. And then this will be h squared times h is h cubed. Minus h times h squared, oh, that's minus h cubed, so those are going to cancel. And then I'll have plus 1/3 h cubed. So the h cubes go away, and you'll have L squared times 1/3 h cubed over h squared. The h squared and the h cubes are going to cancel. I'll write it like this. So this is L squared over h squared times 1/3 h cubed. And the h squared downstairs and the h cubed upstairs will interact, leaving just one copy of h upstairs. So you'll get 1/3 L squared times h. And that is the volume of the pyramid. So these slicing problems can be a little bit tricky. They usually require that you exploit some sort of symmetry somewhere, something like this. But you're going to have to work them on an ad hoc basis. So you're going to have to think very hard about each problem and the symmetry it has and how you can find a formula for the volume of that slice, which is equivalent to saying finding a formula for the area of the cross section. If you know the formula for the volume of a cone, you might be surprised by how similar this is to that. This is 1/3 times the area of the base of the pyramid, L squared, times the height. And the formula for the volume of a cone is 1/3 times pi r squared times the height, which is 1/3 times the area of the base times the height. There's a nice similarity there. And I'll be able to cook that other formula up for you a little later. But this is it. This is the method of slicing. I want to kind of outline for you, I'll give just a second for anybody who's still writing and needing to copy any piece of this down. Outline for you how we cook up that, or sort of the closest thing I can give you to a formula. Amy, be good. Well, let's really briefly talk about solids of revolution. I'll come off to the side here and make sure I can still sketch these things. See if I can remind myself how to do this. Yeah, okay. So I mentioned that the slicing method, the methods that we're talking about today, slicing and disc washer, they all exploit symmetry. Some objects have so much symmetry that we can kind of get around having to, you can kind of generalize and say what you'd do for any of them. Focus, you piece of shit. Okay. So a solid of revolution is what you get by taking a region in the plane and revolving it about some line. So if I were to take this region and spin the whole picture like this, so I'm imagining that the x-axis is like a barbecue spit, As I rotate that, this region will sweep through a three-dimensional region in space. And if I rotate this upper semicircle like this, you can kind of imagine what it would do. It would sweep out like a sphere. Can everybody kind of see that? Or if I were to take a region, so here we would get a sphere. If I were to take a circle centered out here on the positive x-axis away from the origin and rotate it like this, so here's my region, this would sweep out like a donut shape or a torus. It's called something looking kind of like this. My art is bad, so let me see if I've got a, no. Sweep out something like this, right? So you can see if you were to take that circle and rotate it so that it comes out of the page like this and then back in, you would get a torus or a donut shape. So these sort of solids are called solids of revolution. They come from rotating a two-dimensional object about some line, and then imagining that 2D object spinning around and thinking about the path that it sweeps out in space. Objects like that, you can think of their slices in very nice ways. So to show you what I mean, I'm going to do this little example here, and then I'll give you the kind of general formula. So let's find the volume of the solid obtained by rotating the region bounded by y equals x from y equals x and y equals 0 from x equals 0 to 2. So here's the line y equals x. Right here is 2. I want to rotate this region, about the x-axis. So I'm going to take that region and I'm going to spin it around here. When I do that, I'm going to get a cone. I hope you guys can see that. I'll try to draw it to scale here. Right, if I take this region and I spin it around like this, then this whole thing is going to sweep out a solid cone. A cross section of this cone, if I was to come in here and slice and start treating this like the last problem, the cross section of this cone would be a circle or a disc, right? Because it has a little tiny thickness. And you can imagine that disc as coming from a little strip in here being rotated. So here your cross section would be coming from just this strip rotating around the x-axis. I know that the shape of that cross section, if I look at it if I turn it and look at it straight on, like straight down from the tip, is going to be a circle. So that's the thing I call dv, and I can jump straight to that. So again, here is the solid that I'm getting, the little differential solid that I'm getting from rotating just the strip. The volume of this whole thing I call V. The volume of the thing I get just from the strip is my slice. I call that dV. And because of the symmetry here, because this is coming from a solid of rotation, I know that this is going to be a disk. So I know that the cross-sectional area here is going to be pi times the radius squared. So this little disk has a little radius. I'll call that radius capital R. So dV is pi times capital R squared times this little thickness, which is the thickness of this strip, which is dx. So this strip has a little differential thickness that I call dx. And the height of this strip, or the length of this strip, that's the radius. And that, of course, changes depending on where you're looking, right? If I'm looking over here, then my little radius would be very, very small. If I'm looking over here, then my little radius would be very, very big. So R, just like L in the previous example, changes. It's a function of x. So you have to think of this as being at an arbitrary point along your boundary curve. So the x-coordinate, I'll just call x. And since I'm along the line y equals x, the y-coordinate here is also x. So I don't fully understand the question, Rowan. We haven't cooked up any volume formulas yet. This guy right here, this formula is for the volume of the disk. Yeah, not the whole cone. Yeah, okay, yeah. So the formula for dV, I call dV the little differential volume that I get from rotating the little differential strip. So normally the way we would come in here is we would draw the region, we would draw in the strip, and then imagine rotating just the strip. When I rotate just the strip, rather than getting the whole cone, I'll just get this little disk. And this little disk has a little volume that I call dV. D meaning like differential or tiny. dV here is pi r squared, the area of this circle, times dx, the thickness of that disk. So now all we have to do is find r. R is a function of x here. It depends on where I'm looking. And in this case, R, it's the length of the strip. So up here, the y-coordinate is x, and down here, the y-coordinate is 0. This is the point x comma 0 down here. So the length of this strip, the distance from the end of the strip to the axis of rotation, is what I call big R. And here, that is this y value, which is x, minus this y value, which is 0. So dV is pi times, well, r is equal to x. So this is x squared dx. Which means that my total volume, V, the volume of the cone, is going to be the integral from the x value over here to the x value over here. That's the integral from 0 to 2 of dV, which is the integral from 0 to 2 of pi times x squared dx. The antiderivative step here is not hard. This is pi times x cubed over 3, evaluated from 0 to 2. When you plug in x equals 0, everything is 0. When you plug in x equals 2, you get pi times 8 over 3. So that's 8 pi over 3. And what we've just used here is a simplification of the slicing method called the disk method. It's really a special case of the slightly more general thing called the disk washer method. The algorithm, the procedure that you need to run through to solve problems like this: first, sketch the region. Then indicate your axis of rotation. Then you draw a strip perpendicular to the axis of rotation in your region at an arbitrary x location, or at an arbitrary location. So perpendicular to the axis of rotation. If you're rotating about a horizontal line, your strip will go up and down. If you're rotating about a vertical line, your strip would go left to right. Then you imagine rotating just that strip about the axis of rotation. That will give you a little disk, whose volume we call dV. Then you come back to your picture here, and you identify the important elements of dV. Like, okay, so that thickness, that's a dx thickness. The radius of my disk, oh, well, that's the distance from the far end of the strip to the axis of rotation. That's just x here, because I'm along the line y equals x. And my hope is that you can see that this is really the same thing as the slicing method. It's just exploiting a certain amount of symmetry, so you can avoid like coming over here and doing similar triangles and shit like that. Let's look at a slightly more complicated one. Good question. So Eddie asks, why couldn't we have done this with the pyramid? Can anybody help me with that? It's a great question. I'd like to think on that for a minute. There is a very clear answer here. Can anybody think of why we couldn't do this with the pyramid? Yeah, Davis has it. The pyramid isn't a solid of revolution. It's got those flat sides. In other words, the cross section of the pyramid is not a disk. It was a square, right? It was a square with a little thickness. So it's because the symmetries are different. This trick works great, but only for solids of revolution. So only solids that you get by rotating a region. If your solid comes from rotating a planar region, then you can use this. If your solid does not come from that, then you have to back up and do the slicing thing kind of from scratch. So think of the disk and washer methods as being shortcuts in the slicing method that you can apply to solids that have rotational symmetry. Cool, okay. Let's look at a slightly more challenging disk washer problem like this. And then I will outline the kind of formulas that we can use. Imagine I wanted to start with something similar to what we did last time. So let's find the volume of the solid obtained by rotating the region bounded by y equals x and y equals x squared about the x axis. So very similar, Here's y equals x squared. And here's y equals x. They intersect here at 0, and then again over, so at the origin, 0, 0, and again over here at 1, 1. You could find that by setting those two equal to each other and solving. I want to rotate, so I've drawn my region. Now I draw my axis of rotation. I indicate the axis of rotation with a little loop like that, a little loopy arrow. And then I come in here and I draw a strip perpendicular to my axis of rotation in my region. So my region is this. I come in here, my axis of rotation is horizontal, so I'm going to draw my strip at an arbitrary point inside this region, perpendicular to this axis of rotation. So here's my little strip. The thickness of that strip is a dx thickness because this is the x-axis and it's a small change in x that gives me that thickness. The point up here along the curve y equals x is x comma x. And the point down here along y equals x squared is x comma x squared. So the difference between this guy and the previous guy is that there's a gap between the bottom of my strip and the axis of rotation, because my region doesn't come all the way down to the axis of rotation. If I imagine rotating just that strip about this axis, then what I will get is something looking like this. Sorry, my art is bad and I feel bad. So let's try it like that. So if I were to rotate just that strip, I would get a little solid looking like this. Right? This is where the washer in disk washer method comes from, because this guy has a little gap in here. The big radius I call capital R, and the radius in here of the little gap, I call that little r. So this washer is my dV solid now. What is the volume of this washer shape? Well, it's like I took the big disk and I punched out a little disk. So dV here, that's the volume of the big disk, which is pi times big R squared times dx, minus the volume of the little disk, which is pi times little r squared dx. And that can be simplified to pi times big R squared minus little r squared times dx. So here's our procedure, right? We sketch the curves, identify the region, identify the axis of rotation, draw a strip perpendicular to the axis of rotation through my region. Draw the differential solid that you get just by rotating that strip. Label the important figures or important distances on that solid and write down the formula for dV. Now I need to come back to my picture and figure out what the fuck is big R and what the fuck is little r. big R will always be the distance from the furthest end of the strip to the axis of rotation. And little r will always be the distance from the nearer end of the strip to the axis of rotation. You don't have to write that down now. I'll give you those formulas in a minute. I just want you to hear it and try to internalize it. Big R is always the distance from the further end of the strip all the way down to the axis of rotation. And little r is always the distance from the nearer end of the strip all the way down to the axis of rotation. So here, big R, let's see, where do I have room for this? Big R is this distance. And little r is this distance. So what is big R? Well, it's this y value minus this y value down here. Not this one, but this one. So the distance from the top of the strip, or the furthest end of the strip, all the way down to the axis of rotation. The point down here is x comma 0, because I'm along the x-axis. So it's this y value minus this y value. It's x minus 0. And little r is the distance from, it's this y value minus this y value. It's the distance from here to here. So that's x squared minus 0, or just x squared. So again, I'll give you the verbal definitions of big R and little r at the end here when I write down all the formulas. I just want you thinking along with me. Furthest end of the strip, all the way down to the axis of rotation. Here, the axis of rotation is the line y equals 0. It's the x-axis. So that's x all the way down to 0, or just x. And little r is the distance from the nearer end of the strip to the axis of rotation. The nearer end of the strip, that's defined by the curve y equals x squared. So that's x squared minus 0, or just x squared. Now I can plug these in here and integrate this guy to get v. So dv is pi times capital R squared, well that's x squared, minus little r squared, that's x squared squared, that's x to the 4 dx. Therefore, v will always be the integral of dv. I like to draw this step on its own because I use this step to think about my bounds. I'm going to go from the smallest x value in my region, which is 0, all the way up to the largest x value in my region, which is 1. So I think about what x values this strip needs to move through in order to sweep out that whole region. That's from 0 to 1. So I'm going to integrate dv from 0 to 1. And then I plug in for dv. So this will be the integral from 0 to 1 of pi times x squared minus x to the 4 times dx. And then from here, the integral is not hard. So again, before I actually do the integration step, I'd like to take a moment to answer any questions up to this line. So any questions about where these guys come from, where the picture comes from, why this looks like this, why these labels are what they are, anything.
Where does the r equals x and r equals x squared and all that come from?
Let me redraw this nice and big. So my axis of rotation is here, my strip is like right here, yeah? So if this is all taking place at an arbitrary x value in here, r is going to be this distance, capital R, and little r is this distance. Remember, this is the curve y equals x squared, and this is the curve y equals x. So up here, the y value is x. Down here, the y value is 0. So big R, this distance is x minus 0. I want the vertical distance between the point x comma x because my x coordinate is x, and I'm along the line y equals x. So I want the vertical distance from this point to this point. You get that by subtracting the y values, right? You take the big Y value minus the small y value to get that distance. The y value up here is x, and the y value down here is 0, so that distance is x minus 0. And the same sort of thing works here. This point is x comma x squared, because I'm along the curve y equals x squared. So if I want to find this distance, I take this y value minus this y value. So little r is x squared minus 0.
Why is the y value x up at the top?
Because we're along the graph y equals x.
Oh, okay.
Yeah, so that's something we want to have in our brains throughout. If you're along the graph f of x, every point is of the form x comma f of x. So the y value here, that's why you see that label y equals f of x when you look at the graphs, because the points on the graph are x comma whatever your function is. So that's why this guy is x comma x, and that's also why this guy along the parabola is x comma x squared. So Rowan, does that, I think you're asking more or less the same thing she was asking. Little r is this distance. It's the vertical distance from the curve y equals x squared to the line y equals 0. So right here, along the graph y equals x squared, you're at the point x comma x squared. The y value there is the square of the x value. That's what it means to be along the graph y equals x squared. So the y value at this point is x squared because the graph that you're looking at is y equals x squared. And then down here at our axis of rotation, the y value is 0 because everywhere along the x-axis, the y value is 0. So the height here is x squared, the height here is 0, so that distance is x squared minus 0, or just x squared. Is that, are we feeling it? Are we feeling it, Mr. Krabs? Okay. This is a common sticking point, and I want to stay here as long as it takes until we see this. So remember, along the curve y equals f of x, every point is of the form x comma f of x. So along the curve y equals x squared, every point is of the form x comma x squared. That's how I know that this y value right here is x squared. So the distance from there to here is x squared, that y value, minus 0, that y value. And the same thing answers the first question. Why is this distance x? Because we're along the curve y equals x, which means that this y value here is just x, and we're looking for the vertical distance from there to the axis of rotation. The axis of rotation is the x-axis, and along the x-axis, all the y values are 0. So this big vertical distance here is x minus 0, and this little vertical distance here is x squared minus 0. Am I feeling a little bit better about the values of little r and big R? Okay, I am going to come back here and then go ahead and finish up this problem. So drawing these pictures nice and big, really good idea, right? Even this, I drew this pretty large. Even this, still not big enough to really get in there and label everything nice. So if you want to redraw these, I find pretty much every time I solve one of these problems fresh, first time I solve it, I'll draw it. And then I'll be like, this is too cluttered. I can't really see what's going on. And I'll redraw it really big like you saw me do there. That's not a bad thing to do. If you're having a hard time seeing what little r and big R come from in the picture, why they have the values they do, draw your picture extra big. Get in there and label everything. The trick is to label an arbitrary point along your curve as x comma whatever, where the whatever comes from the function that you're given that defines that curve. So the point along y equals x is x comma x, and the point along y equals x squared is x comma x squared. Then you can think about these distances as just subtracting y values. Okay, from here, the integral is not hard. The pi comes out. X squared becomes x cubed over 3 minus x to the 4 becomes x to the 5 over 5. And we evaluate from 0 to 1. When I plug in 0, everything is 0. When I plug in 1, I get pi. Sorry, I lost my pi here. Let's do it like equals pi times, plugging in the 1, we'll get 1/3 minus 1/5. Plugging in 0, everybody is 0. And then 1/3 minus 1/5 is 5/15 minus 3/15 is 2/15. So this will be 2 pi over 15 for the volume. And you'll notice I didn't have to draw the 3D object here, right? The only 3D object I had to draw was this washer. I didn't have to draw the whole solid. What does this solid look like? Well, it's like a cone, but with the inside being all convex, like puffy. So it's a cone that's had like a bit removed from the inside. Your textbook may have a nice picture here, but I'll give just a second more for anybody who's still writing. Any questions on the actual integration here? Yeah, I could see that. Let me I'll flip back to the textbook here and see if I have a picture of something like that. Yeah, here we go. So you can kind of see the shape of this solid. The outside is a cone, but the inside has this like puffy, like bloopy wall. So it's like you've carved out a large piece of the middle of the cone. Good, 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 good. Yeah, the textbook is good. You should read the textbook. I know that for whatever reason, people in mathematics classes get out of the habit of reading the textbook, but the textbook is very good. You should absolutely read it. Before I let you go, because we are almost out of time, I want to give you those formulas in as much generality as I can. So 6.2 formulae. I do also have a module up in Canvas that has a bunch of resources, links to Patrick JMT videos where he solves problems like this, and also links to Paul's online math notes where he solves lots of problems like this. But the most general formulas I can give you for slicing, and these will always work, is that you find a formula for the area of a cross section, call it A of t, and I'm going to use the variable t here because I don't want to force you to one of the coordinate axes. Then dv is A of t times dt. You don't need to type anything for attendance. I'll be using the Zoom history logs, not the chat logs necessarily to take attendance. So just make sure that you've logged in with a name that looks like your real name. And v is the integral of dv from wherever to wherever. And then for the disk washer method, here dv is pi times cap r squared minus little r squared times dt, where cap r is the distance from the far end of the strip to the axis of rotation, and little r is the distance from the near end of the strip to the axis of rotation. And you begin by sketching the region, the axis of rotation, and then drawing the strip perpendicular to the axis of rotation. So this is as close as you can get to formulas that will always work for these sort of problems. You will find some other formulas if you Google around, but they're not safe to use in all problems, and there will be problems both in your homework and on the exams where if you try to use those wonky formulas from the internet, you'll run into trouble. So I really want you to think about it this way. It's not too bad. I promise you this is the fastest way to go about this, and if you practice this, you'll get really good at it. You don't need to do anything for attendance. Like I said, it'll all be fine. I get that from the logs of who's signed into Zoom and when. I can pull that stuff down. So just make sure that you have signed in with something resembling your actual name. Take your time to write down these formulas. If there's anything else that you guys want to ask about before we skedaddle, now would be the time, because we're, I think, just about out of class time, maybe even a little bit over. Okay, so then of course here the last move here would be that v is the integral from a to b of dv, where dv follows that formula. Okay, so if you need more time on the homework from last week, go ahead and WebAssign and submit an extension request, and do me a favor, do that right now so I can get that opened up for you. Finish last week's homework before starting this week's homework. I want to get that knocked out like today, tomorrow at the latest, and then get started on homework 2. Homework 2 will be opening a little bit later today. I'll take just a few minutes here to polish it up, and I'll get it published. But first I'll be going through and checking for extension requests. So if you need more time on last week's homework, submit an extension request. There's no penalty. I'll extend it for 1 week, but you really don't want to fall behind. So take the time today to get caught up, and then look for homework 2 that will be dropping a little later today, and it will be due at the start of class next Monday. On Wednesday, I'm going to introduce another method called the method of cylindrical shells, or my Calc 2 professor called it the onion method. He said because like chopping onions, it will make you cry. It's a little bit tricky, but it's not horrible. It's a lot like the disk washer method. It's just another way of thinking about things. So yeah, that is it. That is what I have for you guys today. Please make sure you finished up homework 1. If you need more time, let me know via an extension request in WebAssign, which I will grant immediately. And then look for homework 2, which will be opening up in just a little bit, containing problems like those we saw today. I do have an office hour this afternoon from 3:30 to 4:30. So if you want to talk more about problem solving, come by and see me there. The links are up in Canvas. Otherwise, I will see you guys on Wednesday, okay? Any last minute stuff? Alrighty then. I will see you guys either in office hours or on Wednesday. I hope you have a lovely rest of your day.